Hello, everyone. Welcome back. So as I said in my previous recording, I will start by introducing the first two models that you will be working with for the first couple of weeks in your discussion labs. And these are the three-phase model and the energy interaction model. So the main ideas will be here is that we will look at the three phases of model, which are solids, liquids, and gases. And we will use a concept of energy conservation, which is described by the energy interaction model, to explain how a certain material goes between the three phases. So let's start with the simple concept of energy and its conservation. So although it does, as you know, when we first start thinking about it and describing it, it will seem like a kind of a very simple idea, but as we will progress through this course, we will see how, although it's simple, it's actually a very powerful idea, and it's going to help us explain a lot of different types of physical phenomena. And 7A, the main focus basically of all of 7A will be conservation of energy and how it applies to these various physical situations. But even in physics 7B and C, you will see the concept of energy conservation coming up over and over again. So what's the main idea? So when we have some physical system and we add some amount of energy to that physical system, where can that energy go? So energy conservation tells us that the only place that that energy can go is to that physical system. So the energy of that physical system must increase by the same amount that we have added. So that energy cannot go anywhere. And then vice versa is true. If instead of adding energy to the system, we decide to remove energy from some physical system, then the energy of that system must decrease. And by how much? By exactly the amount that was removed. So let's think of some simple examples of adding energy. You can add energy to a system, to a glass of water, by heating it. We can remove energy from a glass of water by cooling it. And we'll see many, many examples shortly. So the main idea is that, in a kind of colloquial sense, I'm sure you've heard this many times, is that energy cannot be created or destroyed. We will kind of convert this statement into a mathematical equation soon as well. So you will see how we actually write down that statement in terms of math. And, this kind of statement of conservation of energy is what you will, as I've already mentioned, will be the focus of 7A. All right, so now let's move on to the three-phase model of matter. So these are the three phases. I'm sure you've seen them in your previous science classes. So we have solid phase, liquid phase, and the gas phases. There are more phases in matter, but these are the three that we will focus on in this class. And there are certain mechanisms which we have names for, that take a certain material from one phase to another. So whenever a solid goes into a liquid, so ice into liquid water, we call that melting. When the liquid goes into gas, we call that vaporizing or evaporating. Sometimes the liquid phase is skipped and the solid goes directly into gas, and that's called sublimation. So all these processes that are drawn here with the red arrows, they're processes where energy needed to be added to go to that phase. And we'll think about that a little bit more shortly. But the main idea is, how do we go from, let's say, a liquid to a gas? What's the difference between a liquid and a gas? Well, in a liquid, the atoms or the molecules that comprise it, they're bound together. Where in a gas, we have a bunch of atoms or molecules which are just flying around free. So what's then the difference? What happened in the process of vaporizing is those bonds were broken. And to break something, if you take a stick and you want to break it, what do you have to do? You have to add energy. You have to use your energy to break those bonds. So that's basically the idea. What we're doing when we're going through these phases in that direction from solid to liquid to gas is we're breaking bonds, and that requires energy. So energy is being added. Now we can go in the other direction. We can go from a gas to a liquid by condensing it, and then from a liquid back to a solid by freezing it, or there's also processes that take you straight from gas to solid. That's also called condensing. And when you go another direction, then that's when energy has to be taken out. So when bonds are being formed, energy is removed. When bonds are being broken, energy is added. But that's not really the only part of the story, because we don't just go from solid to liquid. In order to get from solid to liquid, often the solid first has to warm up. It doesn't just turn into liquid at any temperature. So we know, for example, for ice, that's on the, or for H2O, ice doesn't just turn into water at any temperature. It has to get to 0 degrees Celsius first. So this diagram we call the temperature versus energy added diagram. So on the y-axis here, it's temperature. On the x-axis is energy added. So if we move to the right in this direction, when energy is increasing, that's when energy is being added. But you can also interpret it going in the opposite direction. So if we look at it going to the left, that's when we're removing energy. So let's see quickly what it's depicting. And we're going to look at it kind of step by step by looking at these different processes, which are marked A, B, C, and D. So this specific plot of temperature versus energy added it specifically for water, but you can make a plot which has a very similar structure for all types of materials, as you will see in this class. But this one, let's start with the basic one, which is water. So process A, here we just happen to choose our starting position as with a piece of ice which is very cold at minus 30 degrees Celsius. And process A describes that piece of ice going from minus 30 and warming up to 0 degrees Celsius, which is the melting temperature or the freezing point. It has various names of H2O. So that's the temperature exactly when the ice will start turning into liquid water. So, but for now, if we just focus on process A, all that's happening in the process A as we're adding energy is the temperature is increasing. So you could see this red line shows that the temperature is increasing, but there's no phase change, meaning that it's always still ice. It's just getting warmer and warmer. And we give a name to the energy of that ice, which is changing as we add energy. So let's think about that statement of conservation of energy. What did we say? We said that if we add energy to a physical system, then the energy of that physical system must increase by that same amount. So what I'm saying here is that let's give a name to that energy which is changing for this piece of ice, and we'll call that thermal energy. And we're calling it thermal energy because we're associating it with the change in temperature. So thermal energy will always have will be associated with a system which is changing temperature. So when thermal energy changes, so must the temperature, and it has to be changing in order for the temperature to be changing. So in this case, in process A, the thermal energy of H2O is increasing. Now let's look at process B. What's happening here? In all of process B, our material is staying at 0 degrees Celsius. So the temperature is constant. The temperature is not changing, but we are adding energy. So where is that energy going? Well, that energy is going to converting our ice into water. So somewhere in the middle here, what we have is we have a mixed phase. Well, we call it a mixed phase because there's still some ice left, but now there's, as that ice melts, there's more and more water. So like right here at this corner, we're still all ice. Somewhere in the middle, we're half ice, half water. As we add more and more energy, there's more and more water, more and more liquid in our mixed phase until we get to this corner where now we're all water. So in this process B, all the energy is not going to changing the temperature, but it's going to changing the phase. And what exactly is happening when the phase is changing? Bonds are breaking. So all the energy is going into breaking those bonds. And because we're adding energy, then the energy of our system has to be increasing. And we're calling this energy now bond energy. So what we're saying is that in the process B, bond energy of H2O is increasing. We're breaking bonds, we're adding energy, so the bond energy has to go up. All right, and just for completeness, let's go through the rest of this diagram. And process C, kind of similar to process A, except now what we're doing is we're heating up water. Instead of ice, we started 0 degrees Celsius, and as we add energy, the thermal energy of H2O will be increasing here as the temperature is increasing until we get to 100 degrees Celsius. And what's special about 100 degrees Celsius, it's actually not directly marked here, but you could see it's kind of a bit more than 90. That's the boiling temperature of water. So that's when water will start to vaporize. So in process C, what is that energy that's changing? It's thermal energy, because remember, thermal energy changes when there's a change in temperature. And here, as you see throughout the whole process, we have an increase in temperature. So thermal energy of water is increasing. Now process D, here we can see that it's a flat line. So we're staying again at a constant temperature. So as we're adding energy, there's no change in temperature. Where's all that energy going? It's going into breaking bonds. So again, we have bond energy, which is increasing. Also notice that this line is much shorter than this line. And what is that telling us? It's telling us that the amount of energy required to take our piece of ice and convert it to water is much less than the amount of energy that takes to take that same amount of water and convert it into gas. And kind of conceptually, it makes sense, because when we turn a solid into liquid, we're breaking bonds, but we're not really breaking all of them. Liquid is still pretty confined. The atoms or molecules are more free to move around, but they're not completely free. But to go into gas, we're really breaking all interactions between those water molecules. So that requires more energy. And we'll explain all of this in a more mathematical way during the next lecture. Okay, and then process E, here the very last process, because we're just sticking to the solid, liquid, and gas phases. So now all we're left with is making our gas hotter. So by adding, if we continue to add more energy at this corner here, the 100 degrees Celsius, now we've converted all of our water into steam. So we call it steam for when we're specifically talking about water. Again, somewhere in the middle here, we were in the mixed phase. But once we added enough energy and got to this corner, that means we've converted all of our liquid into the steam. And if we continue to add energy, what we're doing is now we're increasing the temperature of our steam above 100 degrees Celsius. So in this case, again, we have thermal energy, which is increasing. All right. Okay, so now I will ask you, kind of after what you've heard me saying about some definitions of bond energy and then thermal energy, so kind of think back. Of course, because this is a recording, you can pause it and think about it, even go back if you're not quite sure. So here's your first question to think about. So a gas, such as water vapor, has less bond energy than a liquid, such as drinking water. So is this true, false? Do they have the same bond energy? Does it depend on the temperature? Or does it depend on whether the substance is vaporizing or condensing? All right, so think about it and I will explain the answer next. All right, so let's go back to our three-phase model. So what did we say? We said that to go from liquid to gas, we needed to add energy. And energy conservation tells us that if we're adding energy to our system, then the energy of that system has to increase. Now, what did we call, what's the name that we gave that energy that was changing when our substance was going through a phase transition? We call that bond energy. So what that means is to go from a liquid to a gas, we had to add energy, and that energy has to increase. So that tells us that the bond energy increases of our H2O as we go in this direction. So what that tells us is that when we started with the liquid, we had less bond energy than we do after we get to the gas phase because our bond energy is increasing. So in fact, a gas has more, not less, bond energy than a liquid. And I really wanted to ask you this question because often conceptually it's a little bit counterintuitive, mostly just I think because of the name bond energy. So don't think about what the actual name says to you, because when you think about bond energy, you might say, okay, a liquid clearly has more bonds, so it must have more bond energy. So don't associate bond energy with how many bonds they are. Associated with, do you require energy to break those bonds, or is energy being removed when you form those bonds? So again, because to go from a liquid to a gas, you need to add energy. So energy is required to break those bonds. Then that energy has to increase of the system. When we're going in the other direction. So, question E kind of doesn't make sense. I mean, how the bond energy change does depend on whether a substance of vaporizing or condensing. But here the question was that the gas has less bond energy than water. So we're just comparing the two phases. So again, initially, often this is conceptually confusing, but as long as you start thinking about it in terms of conservation of energy, did you add energy or remove energy to get from the different phases, then it becomes more clear. Just don't associate the word bond energy with, do you have more bonds or not? Because yes, indeed, liquid water has more bonds than a gas, but a gas has more bond energy. Okay. All right, next. We will also apply the idea of bond energy to not just going through to phase transitions of a specific material, but also to chemical reactions. We can apply the same type of ideas when thinking about chemical reactions. So let me ask you a question here, and then we'll think about it together. So suppose some interaction results in one of the CH bonds in propane, given here, to break. So we have some interaction when we have broken a bond. No new bonds are formed. We've just broken a bond. So did I have to add energy to break the bond, or was energy released by breaking the bond? So read the choices here carefully and think about it. Okay, so the same ideas apply here as they applied when we thought about phase transitions. We said that in order to go from, let's say, solid to a liquid, we had to break bonds, and we had to add energy in order to break them, as we did, let's say, when we also went from a liquid to a gas. So here, what are we doing? We're breaking a bond. Same idea, energy had to be added to break the bond. Energy is not released when bonds are broken. And then it's not a process where first energy is added, then it's released, and so on. This question might be a little bit confusing because you're thinking about propane, which you might connect to combustion, and you know that a combustion reaction results in a release of energy, that you didn't have to add energy, release it. So if you are thinking about this, that was great thinking. But this particular question is just asking you of the process of breaking a bond in propane. In discussion lab, what you're going to do is you're going to look at the entire chemical reaction which is involved in combustion. And then you will see, when you think about all the bonds that are broken, because what is a chemical reaction? You start with a bunch of reactants and you end up with a bunch of products. The reactants are the things that break bonds. So you start with some reactants, the bonds are broken, but then new bonds are formed when the products are formed. But so when bonds are formed, that's when energy is removed. When bonds are broken, that's when energy is added. So the way you're going to think about it, as far as thinking of the whole chemical reaction, whether it required energy being added or removed, is you're going to think about, okay, how much energy did I need to add to break all these bonds, and how much energy was released when the new bonds were formed. And if the energy released is going to be bigger than the energy added, then the whole chemical reaction will result in a release of energy, which is true for combustion. So when you look at all the reactants and products and do the calculation, you will find at the end the energy was released. But this particular question just asked you about breaking a bond in propane, and that in this case, energy had to be added. Okay, so just to quickly summarize this segment of the lecture, what did we introduce here? We introduced the idea of thermal energy, and thermal energy is something that increases when the addition of energy results in a temperature rise. So whenever you see temperature increasing, you conclude that thermal energy increased as well. So we call temperature, you will see this vocabulary in discussion lab. We call temperature the indicator of thermal energy because it's something that you observe in order to conclude something about thermal energy. So if you're observing temperature increasing, you conclude that thermal energy increases, and vice versa is true. If you observe temperature decreasing, then you know that when temperature drops, thermal energy will decrease. We also learned about bond energy, and bond energy increases when there are bonds being broken. So when the addition of energy results in breaking of bonds, in the case of melting, for example, or vaporizing, bond energy decreases when it results in forming of bonds, in the example of freezing or condensing. But we also can use the idea of bond energy and this conservation of energy idea, and we can apply it to chemical reactions. So you'll see some such examples in discussion lab. All right, thank you for listening, and you can move on to the next video where we will go into kind of more mathematical ways of describing conservation of energy as it applies to the three-phase model. Thank you.